Hey, and welcome back. So we're going to look at the different types of crystalline solids. So we can basically say that there's three different kinds of crystalline solids. There are solids made from molecules, and there are solids made from ions, and there are also solids made from atoms. So these are the three different building blocks, I suppose. Okay, that's just in chemistry, so maybe you can have solids made of viruses and solids made of nanoparticles. Well, material science, biology, we'll have to handle those, I'm afraid. So those are our building blocks. So what are they held together by? Well, typically the intermolecular forces that are in between the molecules are things like London dispersion, dipole-dipole, possibly hydrogen bonds. So that's quite a variety, really. That's sort of like saying you can have anything from pennies to $100 bills. So that means that molecules that are held together primarily with London dispersion forces, particularly very small molecules, tend not to be held together very strongly at all. So they have often very low melting points. So something like methane. Solid methane is a very easy to melt substance, right? Its melting point's 100 degrees C in the negative direction. Whereas if you go to things that have, say, dipole-dipole and hydrogen bonds, they can have much higher melting points. Case in point, something like water. So water, very small molecule, right? So very weak London dispersion forces, moderately strong dipole-dipole, but exceptionally strong hydrogen bonding. So you're looking at something that melts at 0 degrees C. Whereas if you go all the way up to sugar, sucrose maybe, so sort of a large organic molecule, lots of places it can hydrogen bond. And so you're looking at melting points that are about 200 degrees C. So a much bigger molar mass means you got much greater London dispersion forces, and you've got a very large number of hydrogen bonds holding these networks of sugar molecules together. Now, I say 200 degrees C, but if you heat sugar in the air, it tends to burn, caramelize, and react rather than melt. So you have to be quite careful there if you're going to try and melt sugar and measure its melting point. Now, we can go to ions. So ions have intermolecular forces that are actually ion-ion. So you might say, well, wait a minute, we didn't talk about those intermolecular forces. Well, you're right, we didn't, but we did in the first semester, right? We called them ionic bonds. And these ionic bonds, right, are thousands of times greater than these intermolecular forces. So a covalent bond, right, is 100 to 1,000 times stronger than, say, a London dispersion force attraction. So they tend to have very high melting points. In general, it is very hard to melt these ionic compounds for the most part. They also tend to be quite brittle, and the reason for that is that the ions are held together in a lattice, and if you hit them with a hammer, the positive and negative ions, right, are normally next to each other. Well, if you kind of push them down one, then the positive and the positives are next to each other. They repel and they crack quite easily. So something like sodium chloride is exceptionally high melting point. So you got the sodium ions and the chloride ions, and they're arranged something like that, and their melting point might be something like 800 degrees Celsius. If you've got something like alumina, alumina is made of aluminum 3 plus ions and oxygen 2 minus ions. So you've got aluminum with a 3 positive surrounded by oxygen with a 2 minus, so a very, very strong attraction there. So remember, the higher the charges, the more strongly attracted they are, the harder it is to melt. So this might melt at, say, 2,000 degrees C. So why are they brittle? So imagine you have this crystal here, and imagine you move this right-hand row by one. Well, now the two chlorides would be next to each other, and they would repel and they would break apart quite easily. And so, you know, if you take these crystals and you hit them with a hammer, right, they will break along these perfect planes and give you these very beautiful crystals. We'll look at the atomic crystals here in a whole separate video, I think.